Hello, everybody. Hey, this is going to be a screencast on how to do these complex circuits. So right here, we're going to see, as in this first one, that we've got a combination of both parallel. These two resistors are in parallel, but these two are in series with R1. So when you have a combination or complex circuit here, you just need to break it down. And the first thing you usually want to do is take the parallel resistors and turn them into an equivalent resistor. So if we look here, we're going to have 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2, etc. Now in this case, we have just this these two, so that's going to be 1/12 plus 1/6. 1/6 is 2/12. 1/12 and 2/12. 1/12 and 2/12 is going to be equal to 3/12. And then we flip that over and we're going to get 12 over 3, which is equal to 4 ohms. Okay, sorry, I was out of the frame there. So our resistance equivalent right here is equal to 4 ohms. Okay, so those 4 ohms are now in series with this R1, and our R total is going to equal to R1 plus R equivalent, which is going to be 8 plus 4, which is going to be 12 ohms. Okay, so right here, we're going to have 12 ohms. And now we can do the total, you guys, we can do the total current, okay? Because when the electricity comes out here, it's going to split off and split off. But right back here, it joins itself. And so since this is the only path back to the battery, we know, not by any calculation, but from just looking at here, that our total current is going to be 3 amps. Now, our total voltage total is going to equal to our current total divided by our resistance total. Okay, so we know that our total current is 3, and we know that our equivalent resistance, sorry, this is not divided, this is times. So voltage is equal to IR. So we're going to have 3, okay, times 12, okay, which is going to be 36 volts. So our total voltage is 36 volts. All right. So now with this 36 volts, right, we know the current through here, which is 3 amps. That's going to be the same here. Once we get here, it's going to split off into less, right? But we do know, because it's coming out only one path to get from here to there, therefore our amperage is 3. So now to calculate our voltage drop there, it's going to be equal to I1R1, okay? And our I is equal to 3. Our resistance is equal to 8, okay? And that's equal to 24 volts, okay? So our voltage across the first one is 24 volts, okay? Now, you guys, we can do the same thing here, and we can say that our voltage drop, okay, is going to be, so if we've got 24 here, and we know and we know 36, so we've got 36 volts here, and we've got 24 here. That means we've only got 12. We've only got 12 right here. So the voltage across 2 and 3 is going to be 12 volts and 12 volts. Okay. Now, what we're not really asking here, is what would be the current? What would be the current through here? Okay. but the current through here would be our current is equal to voltage divided by resistance, which would be 12 divided by 12, which would be 1 amp. So when it comes here, you're going to have 1 amp goes this way. And then we could do 12 divided by 6. 12 divided by 6 is 2 amps. So when it gets here, you're going to split 1 amp and 2 amps, which is equal to a total of 3. Comes around here, you've got 1 amp here and 2 amps there. They come together to merge back into 3. Okay, so that was our example of our first complex circuit. So I'm going to set it for the second one and get right back to you. All right, ladies and gentlemen, we are back with our second circuit here. And so with our second circuit, we have parallel and series. So it's essentially just like the last one. So when we have a parallel and series in the same thing, we want to make sure that we take our parallel circuits and figure out what their equivalent resistance is. So right here, we're going to have 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Okay, so that is going to equal to 1/30 plus 1/30 is equal to 2/30, which is equal to, when we flip it back over, we're going to get 30 over 2, which is going to be 15. It's going to be 15 ohms. Okay. Now, you guys, I know that we did this in both classes, but if you say R equivalent is equal to R1 inverse plus R2 inverse equals inverse. Okay. So on your calculator, you're just going to say 30 inverse plus 30 inverse equals inverse equals, and we get 15. It's probably hard to see there. But that, once you get used to this equation right here, it goes really fast and we don't have to worry about finding a common denominator. With this, it's pretty easy because we already have that easy fractions. All right, so now you guys, we want the total resistance, okay? So the total resistance is going to be the equivalent of these two plus R3, which is going to be 15 for our equivalent, plus 5. So that's going to be a total of 20 ohms. Again, once we have that equivalent, which would be, it would be kind of like writing one that is just 15, so that these two don't exist, and we've got 15 and 5, which would add up to our 20 as if it was in series. Okay. Now, our total current here, current total, is going to be equal to our voltage divided by our equivalent resistance. We know what our total voltage is right there, which is going to be 40, and we know our total resistance is 20. So when we do the math there, when we use our calculator, our total current is going to be 2 amps, 2.0 amps. Okay, now, you guys, that means we're going to have 2 comes this way, right? And right here, and I'll use a different color. You guys, we have this one go this way and this one go this way. Now, you guys, they are of equal resistance. So this 2 amps would have to split into 1 amp and 1 amp. We'll do the math here in a second for that. Okay, but we want to know what the voltage drop across that is. Okay, and we know that the current through 3 is 2 amps because it comes back together, and the voltage drop at 3 is going to be equal to IR, which is going to be equal to 2 times 5, which is going to be 10 volts. Okay, so that means we dropped 10 here, but we had a total of 40. We have a total of 40. So we're going to go 40, but this has got to be 30 because 30 and 10 is equal to our 40. Okay, now again, if we think of this equivalent, okay, if we think of this equivalent is we've got 15 ohms, okay, times 2 amps, that's going to be a voltage drop of 30. And because they're in parallel, that's going to be 30 and 30. Now, if we want to know what the current through this one is, okay, our current, I, is going to be V over R. Our voltage drop is 30. Our resistor, now our specific resistor through 1 is 30, and 30 divided by 30 is equal to 1 amp. The same as that we kind of predicted up here when it split off. You guys, it doesn't always split off evenly. It only splits off evenly because we've got 2 resistors that are the same. Okay, so that means that we're going to have 1 amp through 1 and 1 amp through 2. And 1 plus 1, where they split off, they're going to come back together and give us 2 amps through 3, and that would be our total. Okay, so that is another example there of a complex circuit. So I am going to set up for one more, and then we'll have you guys do the last 3. So, all right, ladies and gentlemen, here is our third example here. Let me try to get rid of that glare. Sorry about that. All right. So anyways, you guys, you'll be able to see that on yours. Now, you guys, we've got 4 resistors here, and they are in a combination of series and parallel. Now, you guys, what we said last time is to kind of take care of the parallel circuits and get the equivalent. So here are 2 parallel ones, but now we can see within one of those parallel branches there, we've got 2 resistors. Now, those 2 resistors are in series because to go from here to here, there's only one path. So when we have only one path, the resistor in series, we just add them together. So we're going to have 6 plus 4. So this equivalent resistance here is going to be 10, which is 6 plus 4. Okay. Now we're going to do the 2 parallel ones. Okay. And that is going to be 10 inverse plus 10 inverse equals inverse, and that is going to be our equivalent resistance, which is going to be 5 ohms, right? So now the other way is 1/10 plus 1/10 is equal to 2/10. We flip that over and we get 10 over 2. That's going to reduce to 5. Okay, so however you do that, it's fine. But if you do this way, when you get weird numbers, it makes it really easy. Okay, so now our equivalent resistance of these 2 is 5 ohms. And now we've got these 2 in series with this one. So now we're going to have 5 plus 5 to get a total resistance of 10. Okay. Now we want the total. Now we want the total current. So total current is equal to voltage total divided by resistance total. Our total voltage across the battery is 20. And our total resistance is 10. So that's going to give us an amperage. That's going to give us an amperage of 2 amps. Okay. Now we can see here that we want to get the total current through here. But now remember, it's starting out with 2 amps right there. There's only one way to go from here to here. So this part right there is in series. So the amperage through 1 is got to be the same as the total because that part is in series. Now, when we get to the voltage through the first one, okay, voltage is going to be current times resistor. That's going to be 2. 2 times 5, okay? So that's going to be 10 volts, okay? So we start with 20 and we drop 10 volts right there. And these two voltages are going to have to drop the rest of the way. So it's going to be 20 minus 10, and that is going to be 10 volts. That is going to be 10 volts. We could also figure that out because we have an equivalent of 5 ohms from here to here when we add these two branches together. And then we can say 2 total amps goes through here. 2 times 5 is going to be 10. So you can either do it by subtraction about adding those things up or do the equation again. All right. So now you guys, we're just going to concentrate. We're just going to concentrate on the current that is going through 4. I'm going to erase this a little bit. Okay. And we know that the voltage drop across here is going to be 10, and we know the resistance is 10. So current through 4 is going to be the voltage drop at 4 divided by the resistance at 4, which is going to be 10, divided by 10 is going to be 1 amp. 1 amp. So we can see here that when we get to this little fork in the road there, we're going to have 1 amp goes this way. Well, there was a total of 2, so we could do the math there, but we're also going to have 1 amp go through this first one as well. The first one as well. So we get 1 and 1, which is equal to 2. It's going to come around here. We're going to get 1 and 1, and we're going to have 2 go back to the end. By the way, if we have 1, our voltage drop across this first one is going to be 1 times 6. We have a 6-volt drop and a 4-volt drop, which would equal our total of 10 that we had for over here. Okay. Anyways, you guys, that is how you're going to do the first 3 examples of these complex circuits. And you guys, we will leave you the rest to do 4, 5, and 6. All right. I hope this was helpful. See you guys next time.